All right, let's dive right in. Today, we're heading deep into one of the most profound ideas in all of physics, the possibility that a hidden geometry is secretly shaping our entire reality from a place we can never, ever see. So, the whole foundation of string theory is that our universe has more dimensions than the ones we walk around in. But that immediately leads to a massive question, maybe the question that this whole field is trying to answer. If these extra dimensions are real, what do they look like? I mean, what is their shape? And it turns out that's not just some trivial detail. Answering that question might just be the key to, well, everything. The shape is unbelievably important. Okay, so here's the core concept. In string theory, all the particles and forces we see, electrons, light, even gravity, they're all just different vibrations of these unimaginably tiny little strings. And kind of like how the note you get from a guitar string depends on how long it is, the note one of these little cosmic strings plays depends entirely on the shape of the space it's vibrating in. So this hidden geometry, it's like a cosmic instruction manual, a kind of DNA that literally dictates the laws of physics themselves. So physicists had this huge job on their hands. They needed to find a shape, a geometry with exactly the right properties to create a universe that looks like ours. And that whole search led them to this incredibly complex and honestly beautiful class of mathematical shapes. So let's meet the star of our show, the Calabi-Yau manifold. Now, these aren't just any old shapes. They're these ridiculously intricate, six-dimensional geometries that just happen to have the precise mathematical toolkit needed to make string theory work. The most important thing is that they allow for a property called supersymmetry, which is this idea that helps keep the whole theory consistent and from falling apart. For all practical purposes, these are the top candidates for the actual arena of reality. And this is where it gets really wild. See, there isn't just one single string theory. There are a few different versions, or flavors, as physicists call them. Two of the big ones are called Type 2A and Type 2B. And the amazing thing is, the kind of physics you get from each theory depends completely on the specific Calabi-Yau shape you put it on. This slide really breaks that down for us. A Calabi-Yau shape has different geometric features you can measure. You can think of it as its overall size versus its intricate, complex shape. Well, for Type Ia theory, the physics it creates, these families of particles called vector multiplets, is determined by one set of those features. But for Type B theory, its physics, which gives you totally different particles called hypermultiplets, is determined by a completely different set of features. This is absolutely the key, so remember it. Different theories actually care about different parts of the geometry. Okay, so we've got our stage, the Calabi-Yau manifold, and we've got our actors, the strings. But what are the rules of the game? What laws does a string have to follow as it moves through this hidden space? Well, those rules are governed by this really rigid mathematical framework called the n=2 superconformal algebra. I know, it's a mouthful, but you can just think of it as the fundamental grammar of string theory. It's like the physics engine running in the background, a set of equations that just make sure the whole theory actually works and doesn't break down into mathematical gibberish. And here's a little peek at those rules. Now, whoa. Don't panic. You absolutely do not need to read or understand this math. The only reason I'm showing you this is to make one simple point. This stuff isn't just philosophical hand-waving. It's all built on this incredibly solid foundation of precise, rigorous mathematics. It's this algebra that gives string theory its power and makes it consistent. All right, we have the arena, we have the rules. And when physicists put those two things together, they stumbled onto something so strange and so powerful, it completely changed how we think about space and reality itself. It led them to ask a question that at first sounds kind of absurd. We just said that the geometry determines the physics, right? But what if two totally different geometries could somehow produce the exact same physics? And the unbelievable answer is yes. This is the huge revelation known as mirror symmetry. Let's walk through it. Imagine universe A. It's built on Type 2A string theory living on a Calabi-Yau shape we'll call X. Now remember, its physics is determined by the properties related to X's size. Now picture a completely different universe B. It's running on Type 2B theory on a totally different Calabi-Yau Y. Its physics is determined by properties related to Y's shape. What physicists found is that for certain pairs of these spaces, the size properties of X are identical to the shape properties of Y and the other way around. And the result? The physics in these two completely different universes are mathematically totally indistinguishable. So let that sink in for a second. The crucial point is the universe doesn't seem to care which geometry is the real one. From the perspective of physics, they are exactly the same. And that suggests that the shape of space-time itself, it might not be as fundamental as we always thought it was. And this isn't just some new interpretation. The source material for this explainer makes the point directly. It says that under these mirror conditions, the two different theories actually become identical. That is a powerful, powerful statement about the deep unity of physics. So this whole mirror symmetry thing, it wasn't just some clever mathematical party trick. No, it was the first real clue that physicists were looking at a much, much bigger picture. As it turns out, this kind of weird equivalence is everywhere in string theory. These relationships are called dualities, and they form this huge, intricate web of connections between ideas that seemed totally separate. Mirror symmetry was just the very first thread they found. And this really shows you how deep the rabbit hole goes. So you start with mirror symmetry, which we just covered, but then physicists found other dualities, like one where you can take the mind-bogglingly complex geometry of a Calabi-Yau and just swap it out for a much simpler, purely algebraic model with zero change to the physics. What this whole web of connections is screaming at us is that the 5 or 6 different string theories, they aren't competing ideas. They're just different points of view, different mathematical ways of describing one single fundamental underlying theory. Okay, so let's boil it all down. What should you take away from all this? Think of it as a story in 4 parts. First, the laws of our universe are probably written in the language of geometry. Second, the alphabet for that language might just be these incredible shapes, these Calabi-Yau manifolds. Third, mirror symmetry shows us that you can have different geometric spellings for the exact same physical reality. And finally, all of these different descriptions, they all seem to point toward a single, deeper truth, a unified theory of everything. And this leaves us with one last, truly provocative thought. For basically all of modern science, we've assumed that the stage of reality, the geometry of spacetime, is the most fundamental thing there is. But if string theory is right, if different geometries can lead to the same physics, it suggests that the stage itself is just a shadow of something even deeper. So the ultimate question isn't just about the shape of the universe anymore. It's about what lies beyond shape itself.